In this video, we will discuss some non-piped water and sanitation technologies and their associated cost. I will not discuss the VIP latrine and other technologies that are well described in the Problems and Solutions 2 documentary video that's part of this week's material for you. As we consider non-piped water technologies, keep in mind which one of the 7 cost components discussed in the last video they address. One of the most common non-pipe solutions is a deep well, sometimes called a borehole, plus a hand pump for lifting water. In this table, I've used the same basic approach that we use to calculate the cost of providing a Hopi household with water and sanitation services. It is important to distinguish this technology where one hand pump is used by many households from a smaller hand pump and hand-dug well, which is cheap enough to be affordable by a single household. Millions of households in South Asia live in regions with shallow groundwater, where hand-dug wells and lightweight, small hand pumps are widely used. Drilling a deep borehole and installing a heavy-duty hand pump to withstand the use of many households every day costs several thousand US. The cost depends on numerous factors such as the remoteness of the community, the conditions of access roads, the number of dry holes anticipated during drilling in the region, and the depth of the well and type of rock encountered. In this table, I've used an estimate of $6,500 US, which is typical of cost I have seen in West Africa. Interestingly, one of the best things to have happened in the rural water sector in sub-Saharan Africa over the last 2 decades is that the price of drilling deep boreholes with hand pumps has fallen dramatically. Can you think why this has happened? Prices have fallen due to the presence of Chinese contractors. These contractors came to build factories, roads, and other infrastructure. They discovered they could drill boreholes much cheaper than Western and local contractors. Chinese contractors started bidding on and winning government contracts to drill boreholes as part of publicly funded rural water supply programs. But $6,500 US is much too expensive for the vast majority of rural households to purchase one for the exclusive use of its household members. So these are public water sources built to be shared by many households. There's an important trade-off between the number of households using a public hand pump and the capital cost per household. The more households that use a public hand pump, the lower per household capital cost, but the longer the average time spent collecting water and the time spent queuing for a turn to use the hand pump. These cost calculations assume that 60 households use one public hand pump. As shown in the table, the cost estimate is about $2.50 per month per household. These costs are much lower than costs for piped water and sanitation services. However, these costs do not include any sanitation facilities, nor do they include costs to the household of the time spent collecting water. And there's a risk that the water will be recontaminated when it is carried home and stored. There are now a whole host of so-called point-of-use technologies for treating drinking and cooking water at a household's dwelling. These point-of-use technologies represent a different treatment approach. With a pipe network, engineers try to secure a raw water supply that is as clean as possible and then provide any additional treatment needed before water is distributed through a pipe network to houses and businesses. In contrast, point-of-use technologies focus on treatment at the home, not at the source. An important advantage of the point-of-use approach is that it can reduce the risk of recontamination as water is transported either by pipe or by container from the source to the house. Of course, millions of people around the world, especially in Asia, have a long tradition of boiling their water before drinking anyway. Boiling is a very effective point-of-use treatment technology, but in many places the monetary and environmental costs are high in terms of fuel consumption and time spent collecting fuel wood. Next, I'm going to describe 5 point-of-use technologies, but this is not an exhaustive list. There are many variations, even of the ones I'm going to discuss. Each has different attributes and may appeal to different households in different places. The simplest and cheapest chemical disinfectant is chlorine. Chlorine is widely available, very effective, and very cheap. but many people find it inconvenient to use and do not like the taste. There are a variety of other disinfection products on the market. One product that's received a lot of publicity is Procter & Gamble's Per Packet. Procter & Gamble packets contain a flocculant and a disinfectant. To treat water with the Per Packet, users open the packet, add the contents to an open bucket containing 10 liters of water, stir for 5 minutes, let the solid settle to the bottom of the bucket. Then they strain the water through a cotton cloth into a second container and wait 20 minutes for the disinfectant to inactivate the microorganisms. Procter & Gamble could not market this product at a commercially viable price, however, and now they give some packets away for free as part of their social responsibility corporate arm. Another water disinfection technology is solar. Solar disinfection essentially involves putting water in a plastic bottle and leaving it in the sun. It's cheap, but obviously it won't work on cloudy days. People may not like to drink water hot also. In my opinion, this is probably best used or thought of as a supplement to other point-of-use treatment technologies. Another point-of-use technology is the ceramic water filter. Ceramic water filters are very popular with NGOs, which often set up local production facilities. There are now local production facilities in many developing countries. These ceramic filters have the advantage of being very cheap. This next slide shows you how they work. They're made with local materials and have a silver coating to reduce microbial contamination. But regular maintenance is required. They have to be scrubbed out when the flow rate is reduced. How often this needs to be done will depend on the turbidity of the water. Some ceramic filters are set up with a siphon, as shown on this slide, and the filtered water drips into a container. The filtration element has a lifespan of about 1 year. The plastic component should last about 5 years. The next point-of-use treatment technology is membrane filtration. The LifeStraw membrane is a filtration product marketed by Vestagard, a Swiss company. These filters come in a variety of different sizes. Chlorine helps to prevent fouling of the membrane and also adds a disinfectant residual. The filter contains a chamber with specially developed resin, which contains iodine that kills bacteria and viruses on contact. The biosand filter is probably the point-of-use technology that I would pick if I had to pick one. It can be operated when required, just once a day if needed. This next slide is a picture that shows you the biosand filter draining into a drinking water bottle. There's a sand that the water filters through and then gravel at the bottom, and there's a biologically active layer at the top which kills bacteria and viruses. The biological filter, on the next slide, you see the biological filter can be made with either a concrete or a plastic container. Transporting these filters to households in rural areas can be a substantial part of the initial cost. One of the problems with a biosand filter is that you do need space for the filter. They're quite big. It's probably not appropriate for households living in densely crowded slums because they just don't have room to devote to the space that's needed to hold a biosand filter. This table presents some of the upfront initial cost of the selected point-of-use technologies that I've obtained from the literature. You can see it's hard to make cost comparisons because the technologies last different lengths of time and treat different amounts of water. The price of Procter & Gamble's Per packets looks very inexpensive, but one packet only treats 10 liters. The biosand filter has a higher upfront cost, but it lasts longer and treats more water per day. This is why I have emphasized the importance of selecting a unit of analysis, either cost per cubic meter or cost per household per month. In this slide, I have tried to express the cost of a biosand filter in terms of US dollars per household per month, using the same basic approach that we use to calculate the cost per month for a Hopi household and the cost per month per household of a deep borehole and hand pump. I estimate that it will cost a household about $1.67 US per month to treat its drinking and cooking water with a biosand filter. This monthly cost per household for the biosand filter seems cheap. But it is only for the water treatment cost, and that's just the third component of our 7 cost components. The household still has to bring raw water to the household and then remove wastewater from the home. Also, this is the cost for drinking and cooking water only. The household does not have the convenience of bathing and washing with clean water. In this table, I've added the cost of a borehole and a sand filter. This combination might be attractive to a household. A borehole could bring the raw water supply closer to the dwelling, reducing the time spent collecting water. The biosand filter could provide protection against recontamination during the transport of water from the borehole to the home and during storage. But the combined cost is up to about $4 US per month, and that doesn't include the cost of improved sanitation facilities. If we added a VIP latrine to the borehole plus the sand filter, the total cost of the 3 technologies probably would be in the range of $7 to $9 US per month. This is getting close to the cost of a simple pipe network. To wrap up, it's important to remember that although non-network solutions are cheaper than pipe networks, they're not free. Also, it's easy to forget that the costs often quoted for non-network technologies are usually just for 1 or 2 of the 7 cost components discussed in our previous video on the cost of pipe networks. For example, all of the point-of-use technologies only address the third cost component in our list of 7. That's treatment to drinking water standards. One question you may want to think about is where a household's financial resources would be best spent, on point-of-use treatment or on the improvement or construction of a pipe network. In the next video, we will discuss the cost of 2 technologies, condominial sewers and desalination plants.